Hmm. Perfect. So we did basic introductory as to what's the difference between simple harmonics, what are the different terms that we use, which is amplitude, phase, uh, phi again, omega is essentially angular frequency, and so on. So do you know all of these already? Yeah. Do you want me to go back to them again?
So I haven't watched the entire video. I mean, I watched the math one, but I didn't watch the physics one. So I mean, I know like most of the terms, but not phi and omega. I know.
Omega, you know. Okay, so quickly I'll do a refresher type thing. So omega is essentially, Harsh, do you want to tell?
What is the angular frequency?
Yeah. So how do we represent angular frequency?
2 pi by time period.
Yes, 2 pi by time period. Okay. Now, how do we get this? We essentially get this from the equation. If we write xt as a cos omega t plus phi. Now, this is the equation for any periodic movement. Okay, any periodic motion can be represented as a sine or a cosine function. We are arbitrarily using cos. Okay, so there's no particular reason why I'm using cos here. I'm just arbitrarily using anything between sine and cos, and either of them are fine. Okay, now this whole thing is called phase. This phi is called a phase constant. Phase constant essentially tells us where are we starting. So on what angle are we starting from? So essentially think of it as a circle, and we'll be doing this today as well. If I'm starting my motion from here, okay, so if I'm rotating something from here, I'm already at phi. So this is the angle I'm starting with, and then the consecutive angle. So after time t, if I go this much, this is my omega t. Okay, so after time t, this much I've covered. So in total this will become omega t plus phi. Okay, so I'm starting at phi, and that is what phase constant is. Okay, this essentially tells us as to, on a graph, if my phase constant is 0, my graph will start from 0. Okay, although I'm taking cos, because I'm taking cos, then my graph will start from here. Okay, if it's something else, say 30-degree, 60-degree, whatever, it will start from somewhere in between, so like this or like this. Okay, and so on. Fine, so that is the difference. Like the phase constant and phase are that's why they are important. um, this will come to right now. Once we get into simple harmonic motion, we'll get back to this. Okay, and this is amplitude. Simply, right, this is the maximum value that the function can attain, because cos and sine function can only have plus or minus 1 as the maximum values, right? Perfect. So let's start with simple harmonic motion. Now, there's a very interesting thing. If I take a pebble and basically connect it with a string, and I rotate it around, revolve it around, it is a uniform circular motion. Yes or no? I mean, if I rotate it as a constant velocity or speed, then it becomes a uniform circular motion. Now, that uniform circular motion, say this is my center, and these are, say, any random positions. If I look at it, so I'm rotating it right now in front of me in this plane, from your angle, when you see my hand going like this, does it seem like it's going in a single line? So my hand goes like this, and then it comes back, and it almost feels like it's moving on a single line. Can you imagine that? Can you visualize that? Right? So say I'm watching this from this side, but I see it as a straight line where this is my center, and let me write it as C so that we do not get confused. And then these positions we can figure out. So this is a little bit, so we basically drop a perpendicular from here, and we'll see this will be somewhere here. This will be somewhere here. And this will be somewhere here. Yes? Right? But now all of these are positions. They are essentially the same pebble that I'm revolving, but these are just the positions of that pebble. So what it feels like is the pebble is going to and fro, to and fro from the center when I look at it from an angle. Okay? And so what we see is simple harmonic motion and uniform circular motion has a lot in common, and we can actually derive simple harmonic motion from uniform circular motion. Did you get this? How they are related to each other and how we can make it work? Okay. So now that's exactly what we are going to do, as to see how we can derive simple harmonic motion and different aspects of it, especially velocity and acceleration, through uniform circular motion. So I'm taking a circle. This is the origin, and this, say, is my starting point. So this is my phi. Okay. Now, my velocity, my particle will be moving that side. The first thing that comes to mind is, how do I get the distance variable, which is x, which is the function of t? How do I get this? Any ideas? How do I get this from just a simple diagram that I have right now?
The circumference, right?
No, I don't want the circumference. I want the relationship. So basically what I want is, say I take a, I drop a perpendicular here, and from here my movement is happening. Basically I want what is the distance getting covered on my simple harmonic motion. Through the uniform circular motion, how can I figure out my movement on the simple harmonic motion? No? Okay. So for that you need to have very clear understanding of what uniform circular motion is. So I'll hopefully you'll get a primer on that as well. See, understand the velocity here will be omega t. Can you understand this? Why it is omega t? Why? What is omega here? Is it the same as what we were using? Is it something else? What is omega t here?
It has to be something else because omega t would mean it can't be that those are not the same units for velocity. So it has to be something different.
Why do you say that?
Because the omega we know it's if I just do unit analysis, it's radians over.
Yes. So it's, this will not be omega t. So here we have in circular motion, if you take circular motion, omega come out as r into v. Okay. Sorry, r into theta. Let me show you how. So delta S will be equals to, do you know what radian is? So I'm just getting confused where what all do you know already, because that's where the problem begins. So do you know what radians are first of all? You do? Okay. But let me tell you again so that there's no miscommunication in between us. So let's understand radians first. And this is on a side note, so do not get confused. Radian is essentially another way that we describe angle, where in a circle, if my arc is the same as the length of my radius, then I say the angle that is getting formed is 1 radian, and I actually represent radian by this little c that you can hopefully see from your side, right? But in general, we remove it because we use it at so many places that we don't have to write radians as a unit. Now, here we are defining this. This is the definition, okay? It's not there anywhere. We are defining it from our perspective. It does not matter what R is. That means the size of the circle can be really big or it can be really small. But once we have the definition, what can we do? We essentially can use unitary method to get the relationship between degrees and radians. So uh, when 360 degrees is there, or rather when 2 pi r is there, the angle that is getting made is 360 degrees. Yes? When I want 1 radian, that implies 2 pi r upon 360 degrees. Sorry, this is 360 upon, my bad, 360 degrees upon 2 pi r. Are you getting it? You look confused. Harsh. Sure? Okay. Uh, Wait a minute. For 2 pi r, which is the circumference, I get 360 degrees, and I want it for r because at r I will have 1 radian. So this is wrong. So for unit, 1 unit length, whatever length I've been taking, this will be the degrees. Now, when the length is r, then my degrees or the angle in degrees would be 2 pi r into r in degrees. This implies what? The angle that would be created here in degrees will be 360, or let's simplify it, 180 upon pi degrees. Here, when the length of the arc is r. Did you understand this? So we started with length of the arc as 2 pi r, and if it's 2 pi r, which is the circumference, the angle at the center will be 360 degrees because we have essentially gone around the circle. Now, if I take 1 unit length, basically unitary method we're using, so 1 unit length arc, then this will be the angle in degrees. Okay, that's why the bracket. Okay, I didn't want to confuse it, so I removed the degrees from here, put a bracket, and then put the degrees again. And now, when I want the arc length to be r, this is my degrees, angle in degrees at the center. What this tells us is that when the arc length is r, this is my angle in degrees, but we've already defined this as 1 radian. So which gives us in degrees should be equals to 1 radian, and which gives us the relationship 180 degree is equals to pi radians. Now this is pi radians, do not forget that. Okay, We usually do not use the C because radians are used so frequently that we can remove that C from there. Okay, but it does not mean 180 degrees is equal to pi. Pi is equal to 3.14. Okay, this will be, if it's just pi, then it's essentially unitless, which is not possible. So this is actually radians, but in general terms, we remove it. Like when we're using phi here, I'm not putting any unit because we understand it's in radians. Now, why am I telling you this? It comes back to omega. Let's understand that. From here, or from here as well, I can get a relationship between length and radius. Okay, I can get a relationship between length and radius. So, when 1 unit length will be equal to this much degrees, or we can also say 1 unit length will be equals to r into theta. 1 unit length will be equals to r into theta. Can this be understood by you? Because length is directly proportional to theta. This is how we are defining it, and this is theta in radians, right? As the as the angle of as the length of the arc changes, my theta is also changing along with it. So my length is directly proportional to theta, right? When my this is directly proportional to theta, now I can remove this proportionality sign, write an arbitrary constant, and take this. Now to fulfill this criteria, I already have one relationship, which is 2 pi r will give me 360. Okay, I'm now writing 360 as 2 pi because we've already found that relationship in radians. So what we can do is length, which is 2 pi r, the circumference, will be equals to k, and theta will be equal to 2 pi in radians, which gives me r as the constant. When I get r as the constant, this thing becomes L is equals to r theta, right? This is why this is important. So here, what are we doing? Length, or S, what is the movement here, is equals to r theta, which is the theta that is forming here. Okay? Now, have you understood the concept of radians now? Are we on the same page how we got this relationship? I'll get omega now in it. When we have S, S is essentially the distance that is getting covered by the particle. Okay, when it is moving on a circle, S is essentially the distance getting covered by the particle. Now, delta S, if I convert this into delta S, it will be equal to delta theta because R is a constant. Okay? Because a minute change in S obviously only results in a minute change in theta, which gives me, and now I'm dividing it by T, which gives me, this becomes what? ds upon dt, which is essentially V, and here I get d theta upon the dt, which is omega. So this is the relationship that we are going to use here. Okay, this is called angular velocity. Angular velocity, which is the same as what we're using over there. Okay, you can see that it is the same thing that we've been using in our relationships as well. Is this understood?
Yes, sir.
You guys are lagging here. I can't hear you properly.
Can you hear us now? Can you
Not
hear me
really.
now?
Yeah, I can hear you, but it's still lagging. Is there a problem when I write it down? No? Okay. It's fine. Okay. Let's come back to this now. Now, what is the distance that I'll be traveling here in a circular motion? What will be the distance that I travel here in the
So
circular motion?
in the circular motion, it should be the circumference, right?
No, circumference means the whole
Yeah.
thing. I'm just saying in say a span of t, okay, if this is t0, if I want to move in t, okay, just for a small amount of time, what is the distance that I will travel? This point will travel.
Oh,
What would be the distance? And it
I
is
mean,
obviously moving on this path, okay? It is obviously moving on this path. Okay, what this is velocity, this is the velocity vector, this is the path that it will be taking. How will it move?
we'll cover that specific arc, no?
Yes, so it will cover a specific arc, say this much. Now as I said earlier, this becomes omega t because this is the added angle that gets that we are moving in that time t, right? So say I moved till here, just for sake of understanding. Now, if I move till here, this becomes cos. I mean, I just have to take the cos of this angle, which is omega t plus phi. Basically, I just need to take the projection of this onto my x-axis so that my distance on the x-axis I can get. नहीं आया समझ में? आज जैसे ही थोड़ा सा टेक्निकल हो रहा है, I see a lot of blank faces. Okay, let me make this even simpler for you. Okay. Say I start here, and this is my initial angle. What I essentially want is when I'm moving this particle, because essentially our argument is the uniform circular motion can be portrayed as a simple harmonic motion, right? So when my particle starts moving on the circle, if I take the projection at each point, say this, or this, or this, what am I getting? Every time I take a projection, I get the position on x-axis. This is x-axis. Yes, and that is exactly what I want because simple harmonic motion, we are only doing the linear version of it right now. So I only want on the x-axis, right? Now, if this is A, again, this is the radius of the circle. If this is A, how do I get this point? How do I get the distance of this point? It simply becomes A cos phi. And it is phi because this is the initial point, right? P is my initial point. Got it? Now, when I go here, say P dash, there is some movement that has been done. And that movement in angle, I can write it as omega t. Right? Omega t angle I've moved in t time period. Okay, this is in t. This is the difference between these two. So I have moved omega t. Phi was already there. This position, how will I give this position now? Same A, because A is the radius. Okay, this is the hypotenuse, and cos but this time the angle would be omega t plus phi. And now we've reached a general form. This same thing will also be applicable for the third case, but this time the t that I will be taking is this time plus the next time period, whatever the time period may be. Okay? But after I get this, once I get this equation, essentially what I'm doing, I can use this to find any point on the x-axis within the circle. So I can find the position of that projection of that point on the x-axis within the circle, right? So this becomes xt, where x is essentially the position of the point. Did you get it now?
Yes.
Yes.
Right? Now, if I had taken sine, suppose if I had taken the projection on y-axis, I now would be taking sine of these angles, right? So if I had taken this, say I write it as yt, that means on the y-axis, this would simply become a sine omega t plus phi, okay? And they are not the same. There is a phase difference of pi by 2, okay? And the phase difference is, if I start this, the phase difference is essentially this angle in between the two axes, which is pi by 2, okay? But they are essentially, the sinusoidal wave would be similar, but with the phase difference. So if I make the sinusoidal wave of this, it will start from here and like this, and this is a, and this will be minus a, okay? This is for xt. And the sinusoidal wave of this, because sine 0 would be 0, so it will start from 0. Do you understand why I'm starting the cos, the function cos as from the top? Why?
Because it's a displaced sine graph, right, by 90 degrees. Because
Sorry.
cos 0 is 1.
Yes. So when I put cos 0 essentially means 1. That means the maximum value a. That's why my at 0, at point 0, because this is also time 0, my angle, sorry, my displacement is at a, right? And the opposite happens for sine, where did I make it right? Yeah, it'll be like this. Okay. If there was a phi, where I'm getting confused was, if there was a phase difference of pi, then they would have cancelled each other. But right now they don't cancel each other completely. Understood? Okay. Now using the same method, we can also find acceleration and velocity. So we'll only stick to x-axis to keep it simple for us. I'll change this a little bit again. Now, the velocity, how will I now get velocity?
I mean, you could differentiate it.
Yes, correct. So that is one way to do it. Okay. So one way to do it is differentiating, but we'll get to differentiating next, because first I want you to understand how we can derive it otherwise as well from this circular motion uh, process that we've figured out. Okay, we need to name you guys because I cannot use the same name. So do you guys have any other names at home or something?
I think people just call me by the last name or him by the last name, whichever.
Acha. No, I would not prefer to do it, but if I don't have an option, then yes, possibly. If you guys have a better idea, I don't mind. If not, then I'll go with this idea. What? No?
Huh? I mean, I don't have a better idea myself. We can ask.
Okay, fine. So, okay, because I hate calling people by their surnames. It's super weird. Um, so, okay. So HG and HR. Let's do that. Okay, that works better for me. Okay, so HG, do you see something that can be done?
So I'm thinking what to do for velocity.
How can you do that? Basically, I want a projection of that velocity. See, this is the velocity vector, right? When you are in a circular motion, the velocity is tangent to the circle, right? So this is the velocity vector. And we just did it. Velocity is equals to r omega. That means this is r omega. Okay? And r here for us is a. Okay, we are taking a as our r just to be consistent with our variables. Okay, so this velocity vector becomes a omega. What do we do now? How do I take a projection of this onto my x-axis? Because x-axis is my SHM framework that I want to use. And let's take this, because again, we are taking this as omega t plus phi, because it's moving and we are already ahead of the first curve. No? No ideas?
No, not no.
Okay, let's do this then. So this is at 90 degrees. If you take the projection of P, it will come out at this point. And if you take the projection of whatever, if even a single top, we'll get this line. Now, you'll see that the angle here will be equal to this angle. That means this is also omega t plus phi. And the reason for that is if I see the first triangle, okay, which is this internal triangle, this will become 90 or pi by 2 minus omega t plus phi. Got it? Are you able to see it? थोड़ा सा ज़्यादा पास में हो गया. Do you want me to make a bigger version?
We can see it, but yeah, I think you just use the triangle property, right? It should add up to 180.
Yeah, it's just a triangle ratio. Yes. Okay. Once you get that, now you can see the opposite end. Both of these lines are parallel to each other because they are 90 to the same base. So this angle becomes an alternate opposite angle. So this is the same as pi by 2 minus omega t plus phi. Yeah. And so once we have this as pi by 2 minus this,
Yeah, so
no?
you just lagged out completely.
Uh, okay, is it fine right now? Just when the nice thing comes up, this internet kind of lags. I don't know why. Okay, let me explain again. what we did is quite simple. And I'm trying to again simplify it so that it doesn't become crummy. This is P. This is my velocity vector, which we have come to know as A omega. And this we are taking as omega t plus phi. Okay. Now, the first projection I'm doing is this. The other one is from this. Okay. Remember, this is not, this is just a vector. Now, I'm also making this line to make it easier. Now, in this triangle, which is PO and P dash, PO P dash, angle, this angle will be pi by 2 minus omega t plus phi, right? And now this angle and this angle are equal. Why are they equal? Because they are alternate opposite angles. Okay, alternate angles between parallel lines, right? Once this angle becomes the same as pi by 2 minus this angle automatically becomes what we want. Got it now? It's fairly simple. Okay. Once we get that, and this is my vector, which becomes my hypotenuse, this line and this line becomes sine of a omega. If this is my angle, this is my hypotenuse, this is the uh, perpendicular opposite to the angle, then I will use sine for that. So this becomes a omega into sine this theta. This becomes our theta as a general. So I will get a omega sine omega t plus phi. Okay, and I will put a negative sign because the direction of the velocity is inside. That means it is opposite to the x-axis. Okay, it will be opposite to the x-axis, and just to reinforce that, I'm using a negative sign because otherwise it won't have a sign, right? So I'm using a negative sign for that, and this becomes my velocity vector. Okay, this becomes my velocity vector, which I can also do by differentiating. How will we differentiate this?
सर हमने differentiation 10th में सीखी थी. So I mean, we know if you differentiate displacement, you'll get velocity. If you differentiate velocity, you'll get acceleration. But it's been some time.
हाँ बोल हर्ष, HG.
सर तो कॉस का डिफरेंशिएशन होता है नेगेटिव साइन,
Yes.
और
No.
अंदर का अगर डिफरेंशिएट करेंगे तो फिर ओमेगा मतलब फाई तो कांस्टेंट है तो जीरो जाएगा, और ओमेगा टी है तो टी टू पावर 1 है तो टी टू पावर मतलब 1 माइनस 1 जाएगा, तो फिर ओमेगा से बाहर मल्टीप्लाई हो जाएगा.
ओके, यस. सो कॉस का जो होता है वो माइनस साइन होता है. सो पहले उसको करेंगे. सो बेसिकली डिफरेंशिएशन में हम we go deeper and deeper with every point. So first will be a sine omega t plus phi, okay, which will give me a negative sign as well. Now this is another function inside of this whole function. So this function को भी मैं differentiate करूँगा. इसको differentiate सिर्फ phi को differentiate करूँगा, it will be 0. इसको differentiate करने में basically क्या होता है, t to the power 1 है तो वो minus 1 हो जाता है. So anything essentially becomes minus. Okay, so if it was t to the power 2, ये हो जाता है 2t 2 minus 1. Okay, which is 2t हो जाता है वो. Okay, so यहाँ पे इसलिए this will become t minus 1 1 minus 1, which will be 0, which is 1. Got it, HR? Yeah. So this becomes a omega sine omega t this. ठीक है, which is the same. So again, remember differentiation is the easier aspect, obviously, if you know differentiation, but the whole idea of this derivation is to make you understand that there is a similarity between uniform circular motion and SHM, and you can use this derivation to your advantage. ठीक है, that means अगर कभी ये नहीं आए, differentiation नहीं आए या भूल गए या हो सकता है 10 साल बाद कभी ये काम आ जाए और तुम्हें नहीं पता, you can derive it from here. Okay, and that happens quite a lot to a lot of engineers. Like मेरे ऐसे ये वाला कभी काम नहीं आया यूनिफॉर्म सर्कुलर मोशन वाला, but there have been so many times where I've gotten stuck with formulas because, well, it I mean, you forget formulas over time, but if you know how to derive it, if you know how to uh, get them by logic and reasoning, then you can derive it 10 years later as well, and it doesn't make a difference. Okay, so till now we have done xt, which is the displacement, which is a cos omega t plus phi, and velocity. These are all functions of time. Sine omega t plus phi. Now, obviously, the next one will be acceleration. How can we derive that as well? Any ideas? Edgy?
Differentiation again.
Yes, that is definitely one way to go. Definitely one way to go, and we'll get to it. But I'd like to use this first and then go there. See, again, all of them might seem like maths, but at the core of it, we are applying physics, the principles of physics. Okay, the calculation is the maths, but the core is physics. क्योंकि ये हमारे पास कैसे आया था? When we understood that velocity is a tangential, I mean, it's tangent to the circle. Okay, similarly, if you understand what kind of acceleration will there be in a uniform circular motion, this will be a piece of cake for you. What
So,
kind?
yeah, so if it's circular motion, there'll be a centripetal force.
Correct. And centripetal force is always the acceleration. Okay, remember the acceleration. The force is usually outside. Okay, I mean, it's inside usually. It can be both ways actually. दोनों चीजें होती हैं. But ठीक है. We can take this inside. The acceleration is always inside, right? Because when you're moving a stone, you are changing the direction. You are changing the direction from this to this to this, which is only possible when there's an acceleration at 90 degree to it. Okay, and this, I mean, ये circular motion में जब हम करेंगे, because we've skipped a little bit of chapters, so I'm not going in detail right now in this. So once you understand that the acceleration will be given by this, and this acceleration is, again, I'm using formulas from earlier only. It's v square upon r, which can also be written as, how can we write this? Omega r, omega square r square, omega square r. Okay, so the acceleration equals this much. Again, the derivation of this we'll learn when we go back to circular motion. Okay, I don't want to do all of that again because it's quite a lengthy derivation in itself. Fine. So the acceleration in the uniform circular motion is given to be this. This is our still the same, omega t plus phi. On the x-axis is simply cos, this is, by the way, omega square r. So omega square a in our case. Remember, again, trying to use the same variable क्योंकि ऐसे confusion होता है, right? Because r जो हम ले रहे हैं, this is the r we essentially is a for us. So The projection essentially becomes omega square, a omega square, cos of, because this is the hypotenuse, this is the angle, and I'm just taking the base. I just want the base. Cos of omega t plus phi. And this will also be minus, because it is in the opposite direction of x-axis, and this will be my at. Okay, and you can differentiate this and see the same thing. So if we differentiate, sine theta will become cos theta. Okay, and this aspect, okay, there's no change. And when we differentiated from cos to sine, there was minus also. Minus cos theta का जो होता है वो minus sin theta होता है. But for sin theta, it is just cos theta. And then we differentiate this as well. ये zero हो जाता है, ये वापस से omega बन जाता है. So we get the same thing, same expression, which is minus a omega square cos omega t plus phi. Okay. Now, can we put them up, all three of them, on graphs and see the relationship between them?
Well, yeah, they're all functions of time, so they will be related to each other.
They should be, yes, and they are obviously. But can you put it onto graph? How will their graph, basically the sinusoidal waves, how will they be different from each other? That's what I'm looking at.
Well, they all, one is cos, sine, cos. They'll all be just phase shifted to some extent.
हाँ, yes. Phase shift तो होगा ही definitely, but क्या, can I make all of them on the same graph? Okay, so let's do these questions now. Can I first of all make all of them on the same graph? Is it possible? See, again, these are very nuanced things that I keep asking. They are very basic, very small little things, but उससे जो clarity आती है वो you won't find anywhere else. Okay, I'm asking, if I say make one single graph, can I accommodate all three of them? Is it even possible? What will be my axis? Axis पे क्या लिखूंगा मैं दोनों को accommodate करने के लिए? Okay, did you not understand my question, or you guys are blank?
So I think x-axis will be t and y-axis will just be y.
Y-axis, how can y-axis just be y?
So you mentioned yesterday the y-axis, or we have displacement, or we can have displacement in different quantities.
Yeah.
Right. So
what are the quantities here?
Yeah, there are three different quantities here. Which, okay, I have to think about this.
See, understand what are x and what is y. X, when we use x, okay, it is essentially the independent variable, which in this case is t. Okay, it is independent. No one controls it. It just keeps on changing on its own. The y, usually what we take on the y-axis, is essentially the dependent variable. That means, अगर t change हो रहा है, if the t changes here, obviously xt will change, because xt is a function of t. Okay, that's what it means. So this, my y-axis will be displacement, and here displacement means just the distance that is moving, because we are just taking x. ठीक है? So displacement just means कि वो कौन से position पे. Okay, and the units of this displacement are length. It's just length के units. So it can be meters, centimeters, whatever we are working with. The maximum is a, minimum is minus a, and cos से है, so I'll start from here like this. Okay, at this point I reach my t, the capital T time period, and obviously the x-axis is t. Okay, the displacement as well it is this way. Understood? Now let's take the next one, which is velocity, which is minus a omega sine omega t plus phi. How will I make this now? Can I can I make the same thing on this uh, chart right now? No. Why not, NG?
So because like our y-axis on this is the displacement, whereas there will be the velocity.
Correct. Correct. This is the basic thing that you have to understand, that I cannot use the same graph because the values that I'll be using, the units that I'll be using are totally different. Okay. So the next one will be velocity. Okay. And now we also want to see the relationship. So I'll make these dotted lines. So you can see the relationship. The x-axis is still t because this is still dependent, but the y-axis now becomes velocity. Maximum now, again, this is another reason because जो हमारा maximum minima है, which is the amplitude, is also different now, which is a omega and minus a omega. Right? Now, when sine is zero, what will be the velocity?
Zero.
Zero.
Oh
Right?
yeah, sorry, yeah.
Yes. When sine is zero, velocity is zero. So we'll be starting from here. And how will it go? Will it go up? Will it go down?
It'll go down, sir.
Correct. So it will be going like this. This is a perfect sinusoidal wave, okay, which starts from zero like this. And you can see the difference as to, you can basically, we can overlap them and see how they are differing in phase as well as quantities. Okay, this quantity will also be different. Similarly, now ideally they should all be made in three, one upon each other. So if you're making it in your notebooks, make it one after the other, okay, so that you can see the overlay clearly. I don't have that space here. Now, what will be my acceleration graph look like? How will my acceleration graph look like?
So the shape will be like the opposite to the displacement one, but the maximum and minimum will change.
Yes, the maximum minima has changed. Shape will be opposite because it will start from minima. Okay, because cos 0 is essentially minus a omega square. So it starts from here and goes like this. Somewhat like this. Okay, it'll probably look better on in your notebooks, hopefully. My board is really small, so it becomes a task to fit in so many different things. Okay, and this gives us a very important relationship and visual relationships between graphs, velocity, sorry, acceleration, velocity, and displacement in a simple harmonic motion, okay, of a particle. So we realize how these three things change with each other accordingly. Okay? And if you put different conditions as to if my omega is fixed and a is fixed and a is changed, how do different things change as well? Okay?
So
Yeah.
each graph is just mapping the previous one's slope, right?
No, we are not mapping the slope.
No, I meant like displacement है और जैसे यहाँ पे wait, हाँ velocity नीचे, acceleration ऊपर है. So acceleration.
नहीं ये अरे
No,
मतलब
you just
इसकी
said
बात कर रहा है ना, this should ideally be below it.
yes.
Okay, yeah, because they are all differentiating. We are essentially differentiating each time, and only then we are getting it. So, but what were you saying?
No, I'm just saying, like, if you look at the velocity graph, at first it has a negative slope,
Yeah.
right? Which is shown, which you can sort of compare to the acceleration graph. Ki pehle it's negative.
Okay. So, see how it works is quite interesting. So here, what is happening? It is going to a minima. Okay, which is this much minus a omega. But at the same time, we see the acceleration increasing. You see the acceleration increasing. Okay, so now you can understand. So at zero the velocity was zero, but as we go down, or that means the object at zero means uh, that's why the third one was also important. So this is at maxima. So let me make this diagram. This is the center point. So if this is, imagine if this is like a spring diagram, this is my amplitude. This is the maximum point it can reach. Okay, because our distance when we start, we are starting at a. Okay, and now you can see at a the velocity is zero, but it is increasing in the opposite direction. Okay, so now it is increasing this side. Okay, it is increasing, and the acceleration is also increasing. I mean, it is coming to zero essentially, right? Here, at the center point, the velocity is the maximum. Okay, the magnitude is maximum. The direction is obviously opposite to what we want. That means it is the maximum over here. Okay, and we'll see this again and again. जब हम next time क्योंकि आज तो हो नहीं पाएगा, because we'll also be talking about force, we'll also be talking about energy of SHM, and so all of these overlap, because here the velocity is the velocity is the maximum, and therefore the kinetic energy is also maximum over here. And next, it again reaches the amplitude. Okay, so it reaches the amplitude, and we'll see the velocity drop to zero, because at the end it drops to zero. Okay, but the acceleration here is again very high, because from here the acceleration is what changes the velocity, right? Because when the velocity is zero, this is the one which changes the direction of velocity and pulls it back. This is the one which changes the velocity and pulls it back. Otherwise तो वो आएगा ही नहीं वापस. Restoring force कैसे होगा? ठीक है? So hopefully, I mean, थोड़ा मतलब तीनों होते तो और अच्छे से समझ में आता तुम लोगों को. But hopefully, you'll be able to understand. See, when you make it like this, I don't know if you can see it. If it's plotted properly, then you can see the difference very clearly. Okay, ki how things change, how with displacement the velocity and acceleration change. And then we'll plot the force as well as the kinetic energy graphs as well, kinetic potential energy graph as well, and then that'll be a lot more fun as well. But in kinetic energy, the time period changes, so that'll also be interesting. Okay, fine. So for today, we'll stop here. कैसा था? I mean, was it tough for you today? We didn't cover. I wanted to cover a lot more today, but शुरू में मेरे को लगा काफी difficulty हो रही थी इन सब में with the equations and stuff. Either of you right now, and then maybe I'll talk to Harsh also, at G also later.
समझ में तो आ गया सर.
समझ में तो आ गया, but थोड़ा difficulty हुई शुरू में.
बीच में थोड़ी सी हाँ.
अच्छा, ठीक है. And what about you, HR?
So it was good. I'm understanding it.
हाँ?
Yeah, I'm understanding it. Yes.
ठीक है.
It makes sense.
Yeah. थोड़ा सा, I mean, this was the only technical part in this chapter. If you've understood this properly, then all the rest, which is the force and the kinetic energy, becomes super simple. Okay, and then we'll take examples of the spring also, how this is applicable over there. Okay, this is a very simplified manner. I don't know if you guys have done this in your school classes. Have you? Like this?
So not this specific diagram, but we have made जैसे कि in mechanics or for that matter momentum velocity, you have just a simple displacement time graph and then
हाँ,
you
वो
have
तो सब लोग ही करते हैं.
तो बस मतलब I don't think we with this chapter we have not done this, but yeah.
But has this diagram improved your understanding,
Oh, definitely.
clarity of understanding?
This one always, yeah, this sort of diagram always clears it up and shows you the relationship between
Yeah,
all three.
all three the things, which is where a lot of people get confused. Okay, even in the motion chapter, this is how things relate to each other. This is where people get confused. Okay, so Harsh, HG, you this is your first class with us, right?
Yes, sir.
Okay, so you'll be attending Atray Sir's class also tomorrow. I hope you know the time and stuff, right? Perfect, perfect. ठीक है. So tell him about how this class was, and I'll talk to you day after once you've gone through both the classes, and then we can talk about it more. ठीक है. And ask your friend also if he wants to join in tomorrow, because I mean, if he wants to join in to physics, then it will be difficult after the next class, because I mean, probably in the next class we'll probably finish this chapter and then we'll only be doing questions. तो उसके बाद फिर मतलब I can only incorporate him once the chapter is complete. ठीक है, which is after the questions and stuff. So I don't want that to happen if he wants to join in. Already काफी late चल रहा है तुम लोग. ठीक है, चलो. Great then. I'll see you guys day after.
Thank you, sir.
Okay. Bye.